Hi, this is Lathal One, and welcome to 709. Please sit back, and I hope you will enjoy our exploration of a variety of data methods during this semester. With this lecture, I want to give you a very basic overview of analytics and give you a sense of the goals of this course. There is no doubt that you have heard about the data revolution. We are dealing with a variety of new terms like analytics, data mining, and data science. Very simply, the term business analytics refers to the skills, technologies, and practices in the exploration of business performance data to gain insights for improvement. Business analytics makes extensive use of data and statistical analysis to discover meaningful patterns to drive decision making. Now, actually, analytics thinking has been used in business settings since the late 1800s, when the father of scientific management, Frederick Taylor, observed work methods for productivity improvements. The quality revolution of the last 20 or 30 years, with the focus on process improvement and the development of Six Sigma approaches to improvement, are part of the business analytics landscape. What is new is the volume of data made available by technology. With a wealth of data, companies are discovering better ways to position themselves. Study after study have demonstrated the power of analytics for business competitiveness. An MIT study shown here found that top performing companies across functional areas were companies that relied heavily on analytics. There are countless examples of the use of analytics in business settings. Let me give you a few classic examples. Consider an example of big data analytics from the retail company Target. Target wanted to capture a very attractive and lucrative market, new parents. New parents spend a lot of time and money shopping and creating new buying habits. And building loyalty among this audience can be very profitable. Since Target captures and records vast amounts of consumer data, they were able to review purchase patterns looking for trends and examine the items couples tended to buy prior to pregnancy, like vitamins, unscented lotion, and hand towels. Through statistical prediction, Target determined the likelihood that couples were pregnant and used these insights to market to these couples well before their child's birth, creating customer loyalty and capturing an extremely valuable market segment. Another fascinating example is Walmart. Walmart looked through all their millions and millions of transactions and found, interestingly enough and consistently, that when a hurricane was approaching their locations, obviously in the south of in Florida, Louisiana, and the south in general, that customers not only bought the obvious flashlights, water, but also consistently bought Pop-Tarts. Now, you might realize that Pop-Tarts is an easy food, it's a quick food, an emergency-based food. But what was really interesting is that they found that customers bought strawberry Pop-Tarts in particular. So Walmart actually leverages on this. With a hurricane coming, Walmart will actually put shelves of strawberry Pop-Tarts at the front of the store, and in the end, they have boosted their revenues. Now, this is an example of analytics in the form of experimentation done on the internet. It is known as A/B testing. Here, companies will basically randomly direct internet browsers to one of two web page designs. Data are then collected on the sales or signups by each design. A statistical analysis will be formed, something as simple as maybe a proportions test, to find which web page, which design offered a higher success rate, and that was the page that is ultimately chosen. Now, here's a fascinating predictive analytics application implemented by Google. It's obviously pre-pandemic. It's related to flu activities. Google was able to spot on predict flu activities by date better than the CDC, and actually was they were able to predict even sooner than the CDC. Google did not use a doctor, a PhD, or any scientist. They simply used the search words used by the Google users. And they came up with this model that you can see in front of us. The blue line is the prediction by date. The yellowish orange line is the actual flu activity. Now, researchers, along with Google, have implemented a similar model as of recent for predicting COVID activity. It's actually quite amazing. Starting with Moneyball and the Oakland A's baseball team in the early 2000s, analytics is spreading through all sports venues to help teams identify undervalued players, predict injuries, and to make game strategies. This slide, interestingly, shows a testimony of the St. Louis Cardinals using the software of this course, JUMP, to conduct their analytics. Here's a great example of where data clashed experts. In 2001, Ted Rugger, a law professor at the University of Pennsylvania, attended a seminar at which two political scientists, Martin and Quinn, made a bold claim. They claimed with a few variables concerning the politics of the case, they could predict how U.S. Supreme Court justices would vote. They analyzed historical data on 628 cases and developed a prediction model based on certain factors, such as the circuit court origin or the ideological direction of the lower court. And from these variables, they developed a simple prediction model. Rugger was unwilling to accept this bold claim. He said the analysis was retrospective and there must have been some sort of manipulation of the predictor variables. So he proposed a challenge, in particular to test the prediction model on future cases. In one corner was the statistical prediction model, and in the other corner were 83 leading law experts and scholars from the top law schools. The battle was on the upcoming cases of 2002. The result? The result was outstanding. In the sense it was a victory for statistics and data. The model predicted 75% of the court's results, whether affirm or reversal, correctly, while the law experts only got 59.1% correct. Now, this notion that experts are not as experts as they think is an interesting issue in itself. I noted Moneyball earlier that showed statistics and data-driven methods are being used by baseball teams, and indeed in the original Moneyball book and movie, it talks about how it outperforms old-time expert scouts. Obviously a victory for statistics. There was a bestseller by Michael Lewis called Moneyball. And this is one of the things that often statistics courses or predictive analytics courses will use as a selling point. You know, statistics can do it. However, in a discussion Michael Lewis had with Richard Thaler, a behavioral economist at the University of Chicago, he told Lewis, you really missed the boat on the message. The real question is not just simply putting on the table that statistics can do it. The real question is, why can't experts get it right? When we realize that experts can't get it right as often as they think they can,
then that really gives the argument that statistics is the better choice. It's a comparative analysis of sorts. This led to Lewis looking into the works of Danny Kahneman and Amos Tversky. Google them. Actually, Lewis wrote a best-selling book called The Undoing Project. It's a fascinating story. I'm not going to be able to talk all about Kahneman and Tversky. Let me just mention a slide here. K&T were psychologists who spent their lives studying how experts in all areas, from medicine to finance to military to sports, how they make decisions in the face of uncertainty. And they repeatedly came with the following conclusions. All of us, experts and others, are just not well equipped to deal with uncertainty. And worse off is that we tend, all of us, myself included, without data, use what we call heuristics, mental heuristics that are biased and leading us to making severely off-mark decisions. And what was fascinating is that Kahneman and Tversky showed that these biases are predictable, that we all have these similar biases. Again, I'll have you Google if you're interested what those biases are. They're fascinating. But what it says in the end, these biases just do not let us make correct decisions, though we think we know what we're doing. And especially experts think they know what they're doing. And when we realize that in a sense, the objective and unbiased approach to correcting for these expert heuristics and biases is data. Data, if properly gathered, is objective and presumably unbiased. Again, that depends on how it's collected. We might talk about that. Here are more examples of the use of analytics. Here is the idea of dynamic pricing, which is used by sports teams from NFL to Major League Baseball to entertainment, like when you go to listen to a band or a singer. You will find that the prices for seats at any of these entertainment venues are not set. They actually can go up or down. Here in the baseball example, the analytics would, after looking at data, they might determine the price should be higher for a given seat, depending on the day of the week, depending on the predicted weather, depending on the opponent, and various other conditions. So this, at times, is often looked as taking advantage of customers, where a customer would say, "Oh my gosh, the seat that I normally sit in is now $30 more. The organization is taking advantage of me." But the counter side to it is that there are days where you can get a good steal on the seat because it's not fixed, and you might get a seat that's $20 or $30 less. And so there is a notion of a win-win application here of analytics. Right here locally, the use of analytics is among companies. Here, for example, Rockwell is known for doing manufacturing analytics, where they're looking at their production lines, the performance, and looking at data to see how to improve on their general performance in manufacturing settings. Here's a Rockwell example that looks almost like the Google example of following food trends, where they're using a sophisticated version of a linear regression model to track energy usage at a certain a site, and you can see how good those energy, the prediction in pink versus the actual usage in green. Analytics has been around for a while. We now think of, AI, machine learning and all that, but analytics actually honestly goes back 100 years. I mean, statistics is part of the analytics. The area of quality, Six Sigma, which has been around way before we might hear the notions of big data and all this kind of stuff, is part of analytics. It's all related to data driven. Um, Here, Whirlpool, actually a Jump customer, uses Jump to drive their Six Sigma initiatives, and you can see how ambitious they are at Whirlpool. They have about 3,000 black belts, and they constantly are training them to problem solve, make predictions, and do data analysis. Here's an interesting example of where Whirlpool uses analytics in their supply chain area. Um, they look at their supply chain base, in which they have hundreds upon hundreds of suppliers of parts to Whirlpool. Any one of those suppliers that might go down could be a disruption to the supply chain. So it's really important for Whirlpool to know if a supplier is up and running to provide parts. So what they looked at is they looked at a whole bunch of data on suppliers, past suppliers, and over time looked at which suppliers actually went bankrupt. If you go bankrupt, obviously you're not a supplier there to feed into the supply chain. Which suppliers were successful, and they came up with a model of predicting the probability of going bankrupt. They use a whole bunch of X variables. You can see that on the right-hand side, publicly available and privately offered information. And they use something called a logistic regression. I'll talk about that toward the end of the course. But here is a model to predict likelihood of going bankrupt. And based on that prediction model, what Whirlpool can do is, well, if a certain supplier has a higher percentage probability of going under based on their predictive model, they can have a contingency plan for that company. Here is good old quality control called SPC, Statistical Process Control, where they're trying to reduce variability and monitor for any unusual events over and above the variability. And it's a basic method of analytics that goes actually 100 years back. It's just control charts. So analytics is finding its place, across the board. We're finding analytics used in marketing, supply chain, finance, accounting, human resources. We now have the phrase people analytics, where human resources are organizations and are using their human resource individuals to implement algorithms for hiring decisions. Now, that's, of course, has to be carefully vetted, these algorithms, so that there's no biases, but still, it's becoming now part of our new norm. Right here at UWM, we have the Connected Systems Institute, which is delivery of data from machines to all the aspects of, as we often say, the Internet of Things, connecting the various things, data feeding upon data, and using these data to sort of how to leverage and gain insight. We have the Data Science Institute, which is a collaboration, UWM, Marquette, and Northwest Mutual, to foster data science knowledge through education and projects.
So when you talk about analytics in terms of topics, there's a wide array of topics. There's no single topic to be what I would call fully versed in analytics. It comes from the domains of IT, information technology, or computer science, statistics, applied math, or operations research. No single area has ownership on analytics. You can see here a Venn diagram of a variety of topics that range from the IT side, things like databases and data warehousing, to the statistics side, like basic stats, regression, forecasting, to the operations research side, which uses various mathematical methods for optimizing, what's the optimal price, what's the optimal inventory level, given the information that we've gleaned from above. Now, for this course, we fall more in the domain, obviously, on the statistics side. So I'm going to kind of fill in that piece. Your other courses that you might take or any journeys you might take to learn analytics would potentially involve the other parts of this display. Here's a similar picture showing the full landscape of analytics as a collection of topics and skills contributed by different disciplines. Our focus will be on the statistical methodology and the software that supports these basic techniques. To really develop as a full-fledged data scientist, you would need to dig deeper into the coverages in mathematics and computer science. That's clearly beyond the scope of this course. My hope is for you to develop a foundation and appreciation for basic statistical concepts. It's up to you if you wish to build upon it in the future.
The need for analytics, it's immense. Now, there's different types of analytics talent needed. There are the deep knowledge analysts that are involved in heavy duty mathematics, statistics, operations research, often having masters or PhDs. There's the IT specialists to work with that data scientist. And then there's where I think maybe most of you might fall, what I would call the business translator, somebody who has enough data savviness, who can communicate with these deep experts in the company, who can link with the data science team, understand the applications, speak to upper management. The demand for folks of this is on the order of 2 to 4 million in the U.S. over the next decade.
Here's some quotes from folks that are in the real world. It's often nice to hear them endorse what we're all learning here. Hal Varian, who was a former professor at Berkeley and now is the chief economist at Google, said, quote, "I keep saying that the sexy job for the next 10 years will be statisticians, and I'm not kidding." Laszlo Bock, who was the former senior vice president at Google in people operations, that's human resources, he's now established his own company, said, "I took statistics at business school and it was transformative for my career. Analytical training gives you a skill set that differentiates you from most people in the labor market." Now, obviously, the analytics revolution has changed the landscape of the academic world in terms of new degrees, courses, both undergraduate and graduate, popping up across all schools. In the MBA world, obviously that's occurring too. I mean, this course is testimony to it, but it never hurts to hear more voices of confirmation for the need to learn this stuff. I'm going to quote here from a recent Wall Street Journal what the dean of Carnegie Mellon's Business School stated. She stated, "The value of the degree is still very, very strong." She means the MBA degree. However, I'm inserting however, "I can see some schools are going to really struggle to keep their MBA programs. The ones that will survive will be the ones that are more management science, using a more skill-based approach, a data approach. They're the ones that will be able to face the disruption that we're all living in our economy right now." So the need for MBA programs to introduce by courses or concentrations analytics is an important survival, to be honest, for MBA programs, because industry is looking for this set of skills in their future hires.
If you're thinking you're too senior or you had an undergraduate course in stats, hey, let's forget about it, I know it, you may think again. Here is a quote from Harvard Business Review that is looking to see that mathematical reasoning, statistical reasoning, is as important to entry level folks as it is to senior executives. You can read here that here's an example from Harvard Business Review, a quote at one company. Though they don't need to be statisticians, we want business users to understand, interpret data metrics and results of statistical models. Capital One, in its hiring practices, are geared toward hiring analytic and numerative employees in every aspect of business. Prospective employees, including, bolded here, senior executives go through a rigorous interviewing process, testing them on mathematical reasoning, logic, and problem solving abilities. So the and further, here's from that same Harvard Business Review: the ability to see data, the big picture, being data literate, competency with data. These are the kinds of skills that you cannot escape. You cannot use the old sort of excuse, I never was good in math, or I never was, this was not my strong suit. It's happening everywhere. And if you don't get yourself upgraded, you may be behind the eight ball in the industry.
Now, I've been focusing on analytics and statistical thinking as it applies to business success, but it honestly is fundamentally important for society as a whole. You know, it can be said that basic literacy is essential for a democratic society. Without the ability to read and write, illiterate citizens remain uninformed and vulnerable to lies and propaganda. The same can be now said about math and stats. In a world rich with data, the abilities to read statistics and think critically about mathematical arguments are now becoming essential skills as being able to read your native language. This notion goes back 100+ years ago in a famous quote by H.G. Wells, who you may know from the famous the War of the Worlds. Um, but this comes from Mankind in the Making. His quote is, and he wrote, "And the time may not be very remote when it will be understood that for complete initiation as an efficient citizen, it is as necessary to be able to compute, to think in averages, maxima, minima, as it is now to be able to read and write." Now, he was talking very elementary statistical thinking, but you get the gist. He's going into the numerate world, into thinking about numbers. Now, H.G. Wells' perspective of 100+ years ago is echoed today. Consider these 21st century quotes. I'll just read through them. Lutsky stated, "Numbers are not only important because they're pervasive because they're important. It is because numbers have both the power to influence and the power to inform. We need to educate citizens to attend to numbers, to understand them, to think thoughtfully and critically about them." In a compact sentence, Clive said, "Statistics is the new grammar." Finally, Gould stated, "To conclude, our understanding of what is the minimal level of statistical knowledge needed by all people, regardless of their profession, professional aspirations, or social class, must be greatly augmented in recognition of the fact that the role played by data in our daily lives is changing dramatically, allows for the development of citizens who can access and analyze data from government and from their own personal sensors in order to answer their own questions, giving them a powerful voice in a democratic society." Now, I can tell you the last several years, COVID in particular of recent, have really demonstrated that so many of folk, citizens to politicians alike, just really cannot think through numbers critically, and understand how to make comparative analyses and draw conclusions from the data. There's a lot to be done in our society. When talking about the inability to read and write, we use the term illiteracy. When it comes to numbers, the inability to think through numbers, deal with numbers, work with numbers, we use the term innumeracy. This is a great example of innumeracy right here on the slide.
It is important to realize there are what I will call two camps of statistical modeling. Leo Breiman of Berkeley calls them two cultures. One is based on traditional statistical inference methods, and the other based on purely the goal of prediction. Inference is the process of using the model to learn about the underlying data generation process, about the underlying population. For example, we may wish to infer the nature of how response variables are associated to input variables. Let's say you work for a real estate company and you want to understand how housing prices vary, how they are affected. You get a set of data from Zillow on various attributes, including number of bedrooms, backyard size, etc. In inference, you ultimately come up with statements like, for every extra 10 feet of backyard space, we can expect the price of the house to increase by $5,000. In this case, we care about the input variables and how they affect the response. We may take that further and delve into the question of why that input variable has that particular amount of effect on that response. With prediction, we're simply wanting to make predictions on the responses based on future input values. Let's take the scenario you work for a car insurance company and you want to predict if future clients will get into an accident. You look at data, run a bunch of models, and find that a person with a lower credit score has a higher likelihood of getting into an accident. Why is that? Well, if you were in an inference mindset, you would delve deeper. But with a prediction mindset, you don't care. It doesn't matter. All you care about is that you've found a pattern in the data that you can exploit for prediction. So if a new customer comes in, has a low credit score, you're going to predict that person to have a higher likelihood of getting in an accident. You raise the insurance prices, end of story. Here are the basic pillars of inference camp versus the prediction camp. In particular, with inference, we're looking at concepts of hypothesis testing, p-values, confidence intervals, and model selection. In prediction, we're also looking at model selection. We'll nuance into issues of underfitting and overfitting, which we also deal with in inference. We'll also discuss prediction performance using techniques such as data splitting. Ultimately, a firm understanding of all these pillars, whether from inference or prediction, will position you well for dealing with data in different contexts with different goals.
Well, we'll need a software to do our number crunching. There's lots of software. First one that might come to mind is Excel. Indeed, Excel can do basic statistical analysis with its built-in functions and its tool pack, the Excel add-in that's in every Windows Excel. So I ask that you add the Excel add-in tool pack because I'll show you some screenshots here and there. For Mac users, it's available free. I think you just have to separately find it on the internet and then bring it into your Mac. With that said, the tool pack and these functions that are in Excel do lack advanced statistical functionality. There are special add-ins by third-party vendors, but there's no obvious industry choice. I will show you here and there some standard Excel, and it never hurts to learn a little more Excel for your career, but it really cannot be our go-to package.
There's a popular package called Tableau, which is well worth learning. We will not cover it in this class,
But if you're venturing into the analytics world, I do recommend learning it because it provides great visualizations that are especially useful when presenting results to a general audience like upper management. It can compute basic summary statistics, some basic predictive modeling, but it's not a comprehensive statistical predictive modeling package. It is primarily dedicated for descriptive analytics. So if Excel and Tableau don't quite do it for us, where do we turn? Well, there are many packages. Two popular packages used by data scientists are R and Python. They're free and open source, uh, and you can do pretty much anything your heart desires when it comes to data analysis, data analytics, data science. They're very popular because they're free and because they're open source. The downside, they are programming languages, and there is a steep learning curve when it comes to using them in a much more comprehensive fashion. There's SAS, which is not a free software, so that's a downside. It's a paid package. You need a license, but it's um, as comprehensive a software out there with a huge array of statistical functions. Now, I'll say that if you're going down the route of really wanting to seriously upgrade yourself in terms of being a analytics data scientist type person, I really would encourage you to learn for sure R and Python and throw in SAS too as one that will definitely not hurt yourself. Here are a couple more packages. Now, again, this is not an exhaustive list. For example, I don't have a package very famous called SPSS here, but let me just note a couple more. Minitab, because I know a lot of people have heard that package. It was originally developed for teaching introductory statistics in university settings. The company since branched out to the corporate world, and they strategically emphasize quality and Six Sigma capabilities. It can do predictive analytics. I say it's a bit weaker relative to the package that we're going to use. In particular, the package we're going to actually use is Jump. It's part of the SAS family. It's very easy to use. It's intuitive. It's point and click. Visuals that it produces are really, on par with Tableau if you really want to push it. It has a strong predictive analytics platform. It is a licensed package. It does come with a cost. You have it free of use here while you're at UWM, but it is an issue post UWM. And that's why I suggest that you might want to, if your company doesn't use Jump, to expand yourself with R and Python if you're interested in furthering your knowledge. For fun, I asked Google's AI machine to give me a summary of some of the packages we just talked about. And the answer is spot on. You can read through it, but basically it's stating that R is viewed as a package that requires a steep learning curve, requires understanding of coding, while Jump is really useful for people who don't program and don't want to invest time in learning a programming language because it's easier to grasp and it's more potent than Minitab. I couldn't have said it better. I can report to you that actually a few years ago, I used R as the primary package for this course. The summary is that it was a bit of a disaster. The students freaked out over learning coding, which is not easy. In R, if you miss a comma, a parentheses, you'll get an error. If you have the wrong case, for example, you put a capital letter when you should have put a lower case letter, you'll get an error. And students were so focused on getting the programming language down that they basically did not have a strong understanding of the concepts. It was clear to me when I was grading exams and quizzes and various things like that. Given that experience, I went back to JUMP, as I am doing now, so that I can focus on the students getting the basic concepts and foundations down. I also reached out to colleagues nationwide in terms of what their experiences are and what are their recommendations. Here's one email sent back to me from the chair of the Decision Sciences Institute focused on data analytics and statistics instruction, and he's a business professor. He states to me, and you can read all of this, that for an MBA audience, he would use Excel and JUMP. He states that he's a big fan of JUMP, and it provides good graphical capabilities and a plethora of data analysis capabilities. He does note that R and Python are valuable to learn if you're going down a very specific analyst job route. However, for MBAs, JUMP provides better understanding of multiple procedures that can make an MBA graduate more effective on the job. He really summarized my experiences and why I'm going to focus on using JUMP. Once you finish this course and have the concepts down, that is a great next step to learning the coding. Now, I want to emphasize the importance of getting concepts and foundations learned first through an experience that my very good friend has had over and over again when dealing with potential job hires. My friend has a PhD in finance. He's a director of research and is a vice president at one of the top New York City investment firms. And he told me when dealing with job applicants for data analytics, data analyst jobs in his department, he would ask this very basic conceptual question. Suppose you know that a variable y is related to two variables, x1 and x2, but you only use x1 in the regression model. What are the issues? And my friend would tell me that time after time, job applicants had no answer, and he even joked that one job applicant, after a long pause, stated, "I can code really well in Python." That is, this job applicant had no answer and had to give some sort of desperate attempt to be considered for this position with that comment that he could code. But obviously the answer reflected that he didn't have basic concepts down. Now, the answer to this is not that deep. In fact, I'll have a slide or two somewhere later in the lectures where we'll learn that this is related, my friend's question is related to what's called omitted variable bias. Namely, by, in this case, not having x2 in the regression, the coefficient for x1 could be biased by virtue of not accounting for the x2 variable. And my friend said if they had given something as simple an answer as that, they were good as gold. But they don't have the basic concepts down. They're coming out of these programs, even at top schools, and these courses, being able to code away in R and Python, but they lack the fundamental concepts. Learn concepts first, then pick up the coding. That's your best route. My focus with the last few slides has been as to why we use JUMP for concept building in this course. I do want to note that JUMP is extensively used in industry, not as much as R and Python, admittedly, but it is used and it is considered a very valuable package to learn in application. Here on this slide, you can see just a few companies that use JUMP routinely. Here's a summary of our course. As I said, it's building concepts and learning how to do basic data analysis using a user-friendly package. Now, we'll need to review basic math in an upcoming lecture. We'll then cover basic descriptive measures and graphs. We'll cover then inference concepts and procedures, which include things like hypothesis testing, p-values, and confidence intervals. Then we'll get into the primary focus of the course, namely predictive modeling, which includes learning in a comprehensive way, regression, applying the modeling techniques to time series. We'll learn something called trees, and we'll end the course on logistic regression. Once you have this firm grasp of statistical and modeling concepts that I hope to provide you, you can then continue your journey by learning to code in R or Python if you wish. If this course is all you need and it gives you a better sense of all these concepts, then the mission is accomplished also in that way. So I look forward to seeing you throughout the semester. We'll be catching you in the next lecture.